That was a fun break. Oh, I think it's for this transition. So now we're going to talk about weight, and there's also a cat. Let's make the cat more to scale. Okay, so let's talk about the radius of Earth. All right, this cat is on the surface of Earth, so it's at the radius of Earth. So this is pretty much everything on Earth, even if you're up at Everest, is about the radius of Earth, because the radius of Earth is much, much bigger than the variability of heights on Earth, okay? Unless you're at like the bottom of the Marianas Trench, then we can start talking about different things, all right? So we know the gravitational force of Earth on the cat looks like this, okay?
So does it pull more on you? Because I thought, like, supposedly if you go to like Mount Everest, it's like you're lighter.
So little g at the top of Mount Everest is going to be different, but like it won't be like
Significant.
16, it'll be like 9.8, like 9.79 instead of 9 like it's not a big change. So for our purposes, to like this first decimal place, everywhere on Earth is essentially the same, okay? Yeah, and you can actually calculate that using this, because what we're getting to is where little g comes from, okay? Because remember, we've also called force of gravity mg. So let's think about this. Which m are we talking about when we talk about mg? If we're dealing with the cat.
The mass of the cat?
Yeah, the mass of the cat. So what do you think all this other stuff becomes? Because we know this is equal to mg. Yeah, that is little g, okay? All that other stuff makes up little g, because you'll notice, does the radius of Earth change depending on the thing that's on Earth? No. Does the mass of the Earth change? No. Does the universal gravitational constant change? No. So g comes from Newton's law of gravitation, and we just shortcut it because it's the same everywhere on Earth, so we don't have to write this whole thing out when we're dealing with things on Earth. Okay? So this is the mass of cat, and then Earth's lowercase g. All right, and that means that lowercase g, if you want to do some algebra, you can set these equal to each other, and you can get that little g for Earth is equal to big G, mass of Earth, divided by radius of Earth squared. So if we wanted to figure out, for instance, little g on the moon, what would we do? What would we need to find? The mass of the moon and the radius of the moon, okay? So you can do this for any celestial object, right? If you have a star, if you have a planet, if you have a moon, you can figure out the mass of that object times the radius of, divided by the radius of that object squared, and then multiplied by the gravitational constant, yes?
But wouldn't the gravitational constant have to change? Like, wouldn't it be different on the moon versus on Earth?
Yes. So, no, the gravitational
Yeah.
constant, big G?
Yeah, big G.
A universal constant. So big G is the same everywhere in the universe. Little g isn't, okay? So yes.
What's the little g? This is m cat little g.
This is 9.8 meters per second squared in this case.
What does that represent?
That's the gravitational acceleration, and this subscript means on Earth, just because now we've sort of scaled out, like most of the problems we've done, it's like you throw a baseball and you can assume you're on Earth, right? So usually we don't have a subscript G here because we're not like, maybe this problem's on the moon. But in this case, now that we're talking about like universal stuff, we could be talking about the moon or Pluto or Saturn, although it's hard to stand on the surface of Saturn because of the gas stuff. Problems. Okay. So anyway, little g is a property of a particular object. Big G is the same everywhere in the universe, okay? So if you get on like a spaceship and go hundreds of light years that way, you'll still be able to use big G, all right? Okay, let's try a quicker question.
Oh yeah, it's 4 points.
I think it's either A or D. Please discuss and we will vote again. Still mostly D, 1A. All right. So the answer is going to be D. So how do we sort this out mathematically? Well, we have that G, little g, is equal to G M over R squared. Okay, so we have this for both planets. So we can write this out. We know that for Earth, this is going to be mass of Earth, radius of Earth, and little g of Earth. We'll call this P for planet. It has G. It has 4 times the mass Earth. And then it's got radius of planet squared. Okay, so the way that we're going to do this is we'll set this up as a ratio, and the reason we do this is we want to get rid of the stuff that's the same. So you can cross out all of the things that are the same. So we're just dividing 2 equations, which is kind of fun. So this, we know these are the same. We can get rid of mass of Earth, okay? So now we can rewrite this. This becomes 1 is equal to 1 over radius Earth squared divided by 4 over radius of the other planet squared. So we can simplify this and we end up with radius of the other planet squared over 4 is equal to 1 over radius of Earth squared. We can end up with radius of planet over radius of Earth, this is all squared, is equal to 4. Okay, we're just doing some algebra. We take the square root of these, we end up with radius of the other planet over radius of Earth, which we can multiply both sides, gives us 2 times the radius of Earth. Okay, so this is the answer D, and all we've done is just cancel stuff out and do some algebra. Okay, so whenever you want to compare 2 things where most things are similar and we know the ratio between different variables but not the actual number, the best way to do it is to set up the equation for one, set up the equation for the other, and just divide them. Okay, that's how we do ratios in physics. Get some G's for different planets. Remember, our universal gravitational constant is true anywhere in the universe. But we have this formula for gravitational acceleration. So let's say we're on a different planet. Here are the accelerations due to gravity for the planets that are local. So we have Mercury is 3.4. We have Venus is about 8.8, so about 1 less than Earth. The Moon is about 1.6. And then something as big as Jupiter is like almost 26. Okay, so all we're doing here is figuring out the mass of that planet, dividing it by the radius squared, and multiplying it by our universal gravitational constant. Okay, so we expect small planets to have smaller g's, big planets, bigger g's. Cool, so let's actually compare the value of g on the top of Mount Everest, which is about 8,848 meters, okay, above the Earth's surface, meaning sea level, to the value of g at sea level. We know the radius of Earth is 6.37 times 10 to the 6 meters, and the mass of the Earth is 5.98 times 10 to the 24th kilograms. So calculate g for sea level, and then calculate g for Mount Everest, and we will compare them and discuss it. So we'll take a couple minutes for you guys to do that calculation, and then we'll talk about it. Okay. We get any answers? 9.8 and 9.83. Yeah. Okay, we'll set this up. So we'll start with just the regular sea level one. So remember, we know that the gravitational constant is just the universal gravitational constant times mass divided by radius squared. So for sea level, we have g, which is 6.67 times 10 to the negative 11th, right? That's big G. Our mass of the Earth, which is 5.98 times 10 to the 24th kilograms. Oh, I forgot to put the units on that. Move that over. So this is newtons meters squared over kilograms squared. And then divide this by the radius of the Earth, which is 6.37 times 10 to the 6th meters. And that's going to give us 9.83 meters per second squared.
What are the units that you wrote for the 6.67?
Oh, this should be squared. What?
What are the units you wrote for the 6.67 Newton meters squared over?
Kilograms squared. That help?
I thought that was like a different unit.
No? I don't know. I don't know how to answer that question. Okay. For the Everest one. Oh, jeez. We basically do the same thing, so I'm just gonna copy this. Okay, but where we're different is down here, so hang on. I hate when it does this. Okay. There we go. So all we're gonna do is just add the height of Everest, which we know is 8,848 meters, to the height of, the radius of Earth. So we're just the radius of Earth plus a little bit more. And that gives us 9.80 meters per second squared. Okay.
So then if we were in the center of the Earth, we'd get crushed if we drill the hole.
Well, I mean, okay, there's a lot of other factors, because like the Earth is made of like a non-solid material once you get deep down. But if you're in the center of the Earth, no, I think you'd be pretty much weightless, because you'd be pulled equally in all directions. It's a completely symmetrical sphere. So if you're in the center of the Earth, you don't feel anything. You don't get crushed, which is weird.
It's weird.
Yeah.
That rain just blew up.
I'm sorry. So if we want to compare things, we could just divide them. So if we divide G Everest divided by G sea level, you can see that it's 9.8. And you'll notice these aren't great estimates of G, because they're a little bit off, because we didn't use these radius and mass values out to as many sig figs as we would have needed to get like a really accurate measurement. But this is just an exercise, so you can see that this little amount doesn't make that big of a difference. So this gives us about 99.7%. So we're only off by like 0.03%, which for most applications is not going to matter, okay? Any questions? Okay, so this is what I mean. Now we've now mathematically proven that everywhere on Earth, unless you're under the sea, which is more complicated, you get pretty much the same G, okay? And even if you're under the sea and you're not that far under the sea, we're good.